Okay, so in this first Alex objective, you're focusing on reading a periodic table entry. And typically what will happen when you read a periodic table entry is you're looking at a couple of things. You normally will have the element's symbol. You'll have a whole number, which is what's referred to as the atomic number, and it's often given the symbol Z. And then you'll have the weighted average atomic mass, and if you're lucky, you may even have the element's name. So it really depends on the periodic table that you use. So I have a preferred periodic table, and you'll probably find, if you look around on the internet, you'll find your own preferred periodic table, but this is the one that I like. And yeah, so here we go, this one here. So you just want to find your preferred periodic table and have that handy when you're doing a test. So you can see in my periodic table, we zoom in on here, it has the atomic number, the atomic symbol, the average atomic mass, and then the name of the element. In the Alex periodic table, it's kind of similar, but you can click on the element and get further information. It's actually interactive. This periodic table is nice because it gives the physical state of the element under standard state conditions, and it also tells you whether it's a metal, semi-metal, or non-metal, which is kind of cool. What this periodic table doesn't have is the North American numbering system, where we've got the groups 1A, 2A, 3A, 4A, etc. It just has the IUPAC numbering system for the groups. So find your favorite periodic table, and then just keep that handy. So it says, write the symbol for every chemical element that has atomic number less than 13 and atomic mass greater than 13.4, and then U is another way of writing atomic mass units. So atomic mass unit, two abbreviations that you'll commonly see, AMU and U, but they are both the same. So we want atomic number less than 13, so it has to come before aluminum, but then we want the mass to be less than 13.4. So if we just kind of like trace back from there, we've got magnesium, that's no good because the mass is 24. Sodium, that's no good, the mass is 23. Neon, that's no good, the mass is 20. Fluorine, the mass is 19. Oxygen, the mass is 16, no good. Nitrogen, getting close, it was 14. So carbon is the first one that has atomic number less than 13 and mass less than 13.4. So the elements are going to be hydrogen, lithium, beryllium, boron, and carbon. And then we want to be careful about the distinction between symbol and name. And in this case, they want a name. So it's going to be hydrogen, helium, lithium, beryllium, boron, and carbon. Okay, so that's it. And remember, whenever we write the symbol for an element, first letter uppercase, second letter lowercase, and that's it. All right, so that's really just being careful, isn't it? It's not really knowing any chemistry that's going to get you to the solution of that problem. Okay, so now it says understanding periods and groups of the periodic table. So it says in what period is chlorine and in what group. So let's have a look. Chlorine is here. So the groups of the columns, so it's in group 17 and then period 3. Okay, So the answer to this, it's in period 3, group 17. Now, if you want to use the North American numbering system for the groups, you could say that it was in group 7A, but it doesn't matter. You can't say it's in group 7. Group 7 is the manganese group. You have to say it's in group 7A. Okay, that's pretty easy again, right? It's just not making a mistake. Just be very careful to read it correctly. Double and triple check that. Okay, organization of the periodic table. So we need a periodic table again. You said you might prefer to use the Alex one. It doesn't really matter. You said read each description in the first column of the table below. If any chemical element with atomic number 92 or less matches the description, check yes and enter the chemical symbol of the element that matches. So we want the symbol, not the name. Otherwise, check no, and then we're going to leave the second column blank. So let's just decide yes or no. So we need to find element 92, which is the last naturally occurring element. It's uranium, right? So a couple of things about the periodic table. Every element that is bigger than bismuth is radioactive, and every element that is bigger than uranium is artificial. So that's kind of interesting, right? So uranium is the last naturally occurring element, and so that's why they often reference that. It's another way of saying, are there any naturally occurring elements that meet this description? All right, so an element in period 3 and group 5A. So we're really looking, is it, so 5A, the A groups are the taller groups, right, on the edges of the periodic table, what we call the representative elements. These are your A groups, and they're just labeled 1A, 2A, 3A, 4A, 5A. So left to right, you're just going 1A, 2A, 3A, 4A, 5A. So there it is, group 5A is your nitrogen group, or it's sometimes referred to as the pnictogons, right? And then we want period 3. So you want to count carefully, 1, 2, 3. So that's where we are. Group 5A, period 3, and are there any elements that are less than 92? Well, it looks like there's a bunch, doesn't it? Or it looks like there's at least one. It looks like there's one. Sorry, not a bunch, but and it's going to be phosphorus, which is 15, right? 15 is clearly less than 92. So P for phosphorus. So yes, and then uppercase P. Now it says a non-metal in group 7A. So this is why my periodic table that I selected is nice, because I can tell at a glance whether it's a non-metal, a metalloid, or a metal. So 7A is the halogens in here. And how many of them are non-metals? Well, quite a few of them. The first 4 are non-metals. And it turns out that they all have atomic number less than 92. So you can pick one of those 4, and I'm just going to pick bromine. So yes, and I'm going to pick bromine. Then it says an element in the nitrogen family with a lower atomic number than carbon. So what do we see here? Where is the nitrogen family? It's here, and then there's carbon, and you see in the nitrogen family, everything has an atomic number greater than 6. So we get a free ride here. The answer to that one is no, lower atomic number than carbon. Being very careful to double check everything. And it says a main group element in period 6. So what we want to recognize is that the main group elements are groups 1A and 2A, and then 3A through 7A. These are called the main group elements. They're also referred to as the representative elements. They're kind of like the ones that are just very vanilla. They do everything in a very predictable manner. These elements in the middle here, in the B groups, these are called the transition elements. And then these ones over here are called the inner transition elements. And then, of course, we know that these guys are the noble gases, right? So we kind of sometimes will talk about that main group for these taller groups that are on the edges of the periodic table, transition elements for these guys in the middle here, and then inner transition elements for these guys here, and then the noble gases are kind of in a category by themselves. So do we have any main group elements in period 6 that have atomic number less than 92? So let's have a look. Period 6, that's a main group. And then these are main groups. And it looks like there's a bunch of them. Period 6, definitely. So you could just pick any one you want. And I'm going to just pick the first one, which would be cesium with atomic number 55. CS. Okay. Now, when you're asked to spell elements, what I would recommend you do is you click on the box in the Alex periodic table and then use the spelling that Alex provides you with. That way you won't get into any weird things with like, disagreements around the spelling between North American and European and the official spelling of these things, okay? All right, identifying the parts of an atom. Complete the table below using the diagram of an atom shown on the right. So it looks like we've got an atom and there's the nucleus, and then there's 2 shells of electrons, and then the nucleus is labeled as A, and then the shells of electrons are labeled as B. So we have to do the names, symbols, charges, approximate mass in AMU, and then the location on the diagram, which is going to be either A or B. So the first thing is we have 3 subatomic particles. We have the proton, we have the electron, and then we have the neutron, like so. All right, and so that's it, right? Now this is the name and this is the symbol. This is the name, this is the symbol, this is the name, this is the symbol. Now when it comes to the charge, the proton has a charge of +1. The electron has a charge of -1. And the neutron has no electrical charges at all. No electrical charge at all. Now the proton has a mass of approximately 1 AMU. The electron has a mass of approximately 0 AMU, and the neutron has a mass of 1 AMU as well. Now, just with reference to this diagram, where are they located? Well, protons and neutrons are in the nucleus, which on this diagram is labeled as A, and then electrons are outside the nucleus, okay? So that's all of the information, right? Well, we've got name, symbol, charge, mass, location for proton, electron, and neutron. So what have we got up here with respect to that? So here's the first one is describing a proton, right? So that would be +1 on the charge, its mass would be 1, and its location would be A. The second one, we're talking about the electron. So E superscript minus would be its symbol, -1 would be its charge, 0 would be its mass, and its location would be B. Now for the third one, we are told that it is in the nucleus, has a mass about 1, and has a charge of +1. So that tells me that it's a proton. So we need to add proton, the name proton, and the symbol for the proton. So in this particular problem, we didn't reference the neutron at all. Okay, so in this problem, we have to count the electron shells in a neutral atom. So what do we mean by neutral? Well, what we really mean is that they're telling you that the number of electrons is equal to the number of protons. And the number of protons that's in an atom is just equal to its atomic number, which we can obtain from its periodic table entry. So that's not too difficult. Now, getting the number of protons is easy if you have the symbol, because we just got to look up the atomic number, right? So for lithium, it has atomic number 3, which means it's got 3 protons. For hydrogen, it has atomic number 1 there. So that means it's got 1 proton, and for cesium, it has atomic number 55. So that means it has 55 protons. Now remember what I said, for a neutral atom, the number of electrons is equal to the number of protons. So we're just going to copy over those numbers. So now it gets kind of a little trickier. We have to think about the number of valence electrons. These are the electrons that are on the outer edge of the atom, the ones that are in its outermost shell. And these are important because when atoms interact with one another, it's going to be by their outer surfaces. So the number of valence electrons determines how the atom is going to react, because that's the outer surface that it presents towards other atoms. And there's a really simple little formula for this, is that the number of valence electrons is just equal to the group number for representative elements. Now, when we say the group number, we mean the group number with the North American numbering system. So if you remember how that goes, it goes like this. It goes 1A, 2A, 3A, all the way across until 8A. So that's the numbering system that we're going to be using to decide the number of valence electrons. And in this case, we can see that hydrogen, lithium, and cesium are all in group 1A, which means they all have 1 valence electron. Now, what we said was that things that are in the same group tend to react in the same manner. And so that makes sense now. The reason that they're reacting similarly is because they have the same number of valence electrons. Now, what about the number of electron shells? Well, the number of electron shells is simply equal to your period number. And so that makes things quite easy. So lithium is in period 2, so it has 2 electron shells. Hydrogen is in period 1, so it has 1 electron shell, and cesium is in period 6, so it has 6 electron shells. And if I was to write out the electron configuration for each of these elements, hydrogen has electron configuration 1, you can see that it has only 1 shell, and that is the first shell. Lithium has electron configuration 1s2, 2s1, so you can see that it has 2 shells. It has that n equals 1 shell and the n equals 2 shells, so it has 2 shells. Now cesium, I've got to go all the way out to 55 electrons, and I'll see if I can do it. It goes 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s1. And so you can see that it has the first shell, the second shell, the third shell, the fourth shell, the fifth shell, and then finally we've got shell number 6. All right, so it has 6 different shells. Okay, but we don't need to write out the electron configuration to decide that. We can just look at the period number. All right, so that's really one of the really powerful things about the periodic table. So the period number indicates the number of electron shells, the number of valence electrons we're getting from the group number, right? The total number of electrons we're getting from the atomic number, and the total number of protons we're also getting from the atomic number. So what we're really recognizing here is how to use the periodic table to how to use the periodic table to understand how electrons and protons are organized in an atom. Okay, so here's another one, but we only have the one element here. It says how many protons are in a neutral atom of helium and how many electrons. So we know that our atomic number is equal to our number of protons, and for a neutral atom that will also be equal to our number of electrons. So if I look at the periodic table entry for helium, I will see that the atomic number is 2. Okay, there is the atomic number for helium. So I know that it has 2 protons and 2 electrons. Pretty easy going. Okay, how many protons and neutrons are in an atom of xenon 136? So the 136 on the end there is what we call the mass number, often given the abbreviation uppercase A. And A is equal to your number of neutrons plus the number of protons. Now, if I go to the periodic table and I look up xenon, I can get the atomic number, which is my number of protons. So let's just do that now. Xenon is a noble gas. It's right at the bottom here, and the atomic number is 54. So 54 is my number of protons. So if I was to do the number of neutrons plus protons minus the number of protons, hopefully you can see what is left is the number of neutrons. There you go. So what you want to really take in mind is that the mass number minus the atomic number gives you the number of neutrons. So 136 minus 54 is going to give me my number of neutrons. 136 minus 54 equals 82. Okay, 82 it is. Put that in normal mode. There we go. Alright, 82. Okay, So that's easy going. So my protons, I'm just going to get that from the periodic table. It's just the atomic number, and then my number of neutrons, 82, and add those two things together should give me 136, which it does. Okay. Finding atomic mass from isotope mass and natural abundance. Okay, so this is pretty easy. Atomic mass is equal to, now what you have to do is you have to add together for every isotope the mass of isotope times its percent abundance, often called the natural abundance, divided by 100. And you're going to do that for every isotope, and then you're going to add them together, which often we indicate with this like big letter. It's called sigma, which means sum for every term of the following type. So basically what that means is I'm going to do this in my case for every isotope that's present. There were 2 of them. So I'm going to do it for every isotope. I'm going to calculate that, and then I'm going to add them all together. So the first one, the mass is 95.9, and the abundance is 97.1, and I got to divide that by 100. And then I do that for the second one. I got 97.9, and then I got to times that by the abundance divided by 100. So the key thing to recognize here is it's mostly the one that is near 96. So it's going to come out a lot closer to 96 than it is to 98. So it's mostly the one that's 96 with a little bit of the 98. So I'm expecting it's probably going to be like a little bit bigger than 96. So like maybe it's going to be like 96.2. Right? It's going to be a little bit bigger than that number, but not much. So that's what I want to, that's what I want to think about, because it's like 97% of that one, right? So now we just got to kind of put it all in without making an error. So 95.9 times 97.1 on 100 plus so 97 point, well actually let's put that in parentheses, 97.9 times 2.9 on 100. Parentheses. I think I'm going to go back. I'm going to put that first term in parentheses, right? Just a minute. There we go. Okay. So I put both of those terms in parentheses just like I wrote it on the whiteboard. There we are. And 95.958, which is sensible, right? That's what, it's pretty close to that. 95.958, okay. Now I want to read the instructions about how I would am wanting to round this off. Use these measurements to complete the entry for ruthenium in the periodic table that would be used on this planet where it has this distribution of the isotopes. Round your entry for the atomic mass to 3 significant figures. So I want to cut this off here. So that means the 9 would go up by 1, so it would become 96.0 AMU to 3 significant figures. So in the periodic table, the atomic number goes there and the mass goes underneath there. So we need to find the atomic number for ruthenium. So grab my periodic table. Move that down somewhere sensible. And find ruthenium. There we go. Ruthenium is element number 44. Now that's not changing. So 44 goes there. But what was changing was the distribution of the isotopes. And so that's going to affect the mass. And so it's going to be 96.0. So when we look at the whole universe, the distribution of isotopes of ruthenium averages out to 101.1, right, when we look at the entire universe. But when we look at this just one planet, and we based our measurements just on the isotopes that are present on this planet, what we find is that the distribution of the isotopes is 96.0 on average, all right? So it's slightly different. So this question is asking us to count the number of valence electrons in a neutral atom. And so let's remember that for a neutral atom, the number of protons equals the total number of electrons, and that's going to be equal to the atomic number. Now, we don't want the total number of electrons, we just want the valence electrons, the ones that are on the outer edge of the atom. And the important thing to recognize here is that for representative elements, or also called main group elements, the valence electrons equals the group number, but only when we write the group number using the traditional North American numbering system. So for the representative elements, that works out like this. We're going to just label 1A on the far left, and then these are not representative elements, are they? Through to 8A on the far right. So we're interested in the number of valence electrons that iodine has, and so iodine is in group 7A. And group 7A means that it has 7 valence electrons. There we go. So 7 electrons that are on the outer edge of that atom. Okay. So, grabbing a periodic table again. It says fill in the missing information about the atoms in the table below. And we have a couple of things here. We've got the symbol and we have to decide the number of protons. Now we know this, right? The atomic number equals the number of protons, and it also equals the total number of electrons. So we have a plan for the first two columns. All we have to do is look these symbols up in the periodic table and get that atomic number. That's going to be pretty easy. Now the valence electrons is simply equal to the group number when we use the North American numbering system for the group number. So we've got a plan for the valence electrons. Now the number of electron shells here, we haven't talked about that before, but the number of shells is simply equal to the period number. So this question is really all about understanding how the periodic table works. So we've got strontium, beryllium, magnesium, which are all in group 2A. There they all are. So the first thing to recognize is that they are in group 2A, all of them. So that means they all have 2 valence electrons. So that was quite easy. Now let's have a look at the shell number. So for beryllium it's 2, for magnesium it's 3, and for strontium it is 5. So 5 for the number of shells, 2 and 3. So that was easy. And then now we just have to get the atomic number, and that's going to give us our number of protons and also our total number of electrons. So for strontium, the atomic number is 38. For beryllium, the atomic number is 4. And then for magnesium, it's 12. 12. Okay. So this is the information that we used. The number of protons is simply equal to the atomic number, and the total number of electrons is also equal to the atomic number. That's how we got that. The number of valence electrons is equal to the group number. That's how we got that. And then the number of shells is equal to the period number. Now, if I wrote out the 4 electron configuration of these elements, we could see that. So for strontium, we want to write out the electron configuration that has 38 valence electrons. So it would go like this: 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2. And so where is the outer shell? Well, it's the 5th shell, and it has 2 electrons in it. So the number of electron shells is correct, and the number of valence electrons is also correct. But I didn't have to write that all out. I just got that from the period number and the group number. You see how easy that was? All right? So if I look at beryllium, 1s2, 2s2, we can see it has 1, 2 shells, just like we wrote there, and then it has 2 valence electrons, 2 electrons in that outermost shell. So again, we didn't have to write out the whole electron configuration to get that. What about magnesium? 1s2, 2s2, 2p6, 3s2. That takes me up to 12 electrons. So there are 1, 2, 3 shells, and that last shell has 2 electrons in it. So 3 electron shells with 2 valence electrons in. But again, we didn't do the whole electron configuration. We just looked at where the element was on the periodic table and took note of its period and group. Okay, so that gets us all the way through the objectives for this week. So I hope you found that helpful, and good luck with your test.